I'm Ken Tate. I'm the Director of Engagement and External Relations for the Department of Computer Science, and I want to welcome everybody to this. This is the LabCorp Leadership in Technology Speaker Series, and if you're wondering why you can't hear me through the speakers, this microphone is purely for the folks that are joining us online, and so we welcome you from wherever you are joining us tonight. So we usually have a really good crowd here in the room, and then a good 70 to 80 plus people joining us virtually. This is the third talk, the final talk for this fall. We will have it again next semester, so we invite you back. I especially want to welcome any first-time visitors that we have. A couple of pre-talk announcements. Now would be a great time to silence cell phones or anything that might be a distraction. And I already pointed out that we're not only streaming this live, but we're also videotaping it. So if you need to go back and check any of the material, you can do that. And usually it's about a week before we get those up and running. So, if you've not been to one of these before, I could just tell you that this series has become one of the premier series at NC State. It started about 14 years ago. It was under the Fidelity Investments name, and then LabCorp came in and generously picked up the sponsorship for 3 years just a couple of years ago. So we want to thank them for their generous support to keep this going. We have tackled every topic you can possibly imagine, but everything is always focused on the unique world of leadership and technology, and it is quite unique. Tonight, we're going to turn our attention to how computer science can be used in the world, and in particular, AI and machine learning, and how it can be used to radically improve healthcare around the world. Tonight, we're honored to welcome with us Dr. Amir Bahmani. He's our special guest speaker, and Amir is the director of Stanford Deep Data Research Computing Center, and he's a lecturer at Stanford University. He's been working on distributed and parallel computing applications since 2008. Currently, Amir is an active researcher in the VA Million Veteran Program, the Human Tumor Atlas Network, the Human Biomolecular Atlas Program. You're involved in so many things. The Stanford Metabolic Health Care Center and Integrated Personal Omics Profiling. And this is truly a homecoming. I know we had homecoming week last week, but this is truly a homecoming for Amir. He completed his MS and his PhD here at NC State, where he studied under Dr. Frank Mueller, who's with us tonight. So, Dr. Mueller, thank you for coming. On Thursday evening, he will be honored by the department as the recipient of the 2002 CSC Alumni Rising Star Award. So, ladies and gentlemen, please join me in welcoming back to NC State's campus our special guest speaker tonight, Dr. Amir Bahmani. Amir?
Thank you so much, Ken. Appreciate it. Hi, everyone. It's great to be back at NC State. It's an honor and privilege to be here. My name is Amir Bahmani. I'm a computer scientist and a lecturer at Stanford School of Medicine. And today I'm here to talk about deep data needs and challenges in precision health. So here's the outline of my presentation. I will share one personal story first about myself, my background. Then I'm going to talk about precision medicine needs and challenges. Then I will go through some disruptive solutions that I develop at Stanford School of Medicine. And then again, I will share another personal story about collaboration and some more technical projects. And finally, I will go through one more story, serendipity and mentorship. And finally, I will talk about education. So here we go, life of an international student. I was born and raised in Iran, and many of you probably know these days that a country that people are protesting these days, and their slogan is women, life, and freedom. And in 2010, my wife Someira and I came to the States for a better life, of course, and for an opportunity. We had to go to another country, a third country, to apply for student visa. We went to Cyprus because there is no U.S. embassy in Iran. And then we got our visa, and our first destination was Missouri University of Science and Technology. And then in 2012, I transferred to North Carolina State University, and I met two wonderful people, Dr. Frank Mueller, my supervisor, and Dr. Douglas Rees, who was the graduate coordinator at that time. And then I joined Mueller Lab, and I was working on Scala Trace, scalable tracing toolset for large-scale MPI applications. In 2013, my wife, Somera, she was admitted to NC State, and as an international student, if you want to change your visa type from F2 to F1, you have to leave the country. As an Iranian, we have a single entry visa, so we left the country, we went to Dubai, and then they told us like it will take 2 weeks to get your visa. So we went to Iran, you're waiting, it's been 1 month, now it's 45 days. And you know, I got my clearance, my visa, I returned to the States. My wife, she's stuck there in Iran. So for 4 months, you know, we were separated, and it was really hard. I remember I went to Dole's airport, Washington, D.C. to pick her up in December, and she told me that I have some back pain. And we would go to NC State Health Center, and they would tell us that she's studying a lot, she has stress, and I'll talk about it. When you walk into the physician office, they have 15 minutes to figure you out. Okay, we'll talk about it. But in March 2014, at the end of March, she had so much pain, so we had to rush into the hospital, and it turned out that her gallbladder was inflamed. And after they took it out, they told us that she has stage 4 cancer. So Somera passed away 5 months after that, and she asked me 2 things. One is to continue my PhD, finish my study. The second thing was like, will you be able to, bury my remains back in Iran? So I knew that it's going to be hard. I went to Iran, and first to Turkey and then to Iran, and then after conducting her funeral, after 7 days, I went to Armenia, another country, thinking that, okay, this time probably would take less time. They told me that it would take 2 weeks, so I went to Iran, and it's been 1 month, 2 months, and now it's 80 days. The problem was I couldn't stay in Iran also because I had to go to military service as an international student. We cannot stay in Iran. Anywho, it's almost 85 days, so I left Iran to Turkey. I was in Turkey, and I received a message that if I do not return back by census date, I will lose my funding also. So it was just like reached the rock bottom of my career. Lost my wife, of course, and now I'm gonna lose my career. It was very hard that night, I remember. But, I tried everything, and then, that night was really hard, but woke up in the morning, and I got an email from U.S. Embassy in Armenia that, hey, come here and pick up your visa. Now I'm in Turkey. There is no way to go to Armenia. I cannot go to Iran because of military service. I cannot come to U.S. because of my visa. So what should I do? I went to Russia. As a transfer passenger, I went there, and I was questioned, hey, what are you doing here? You're coming from Turkey, you're an Iranian student, what are you doing in U.S.? Of course, all those questions, and eventually I got to Armenia, picked up my visa, and went to Abu Dhabi and returned to the United States. So this is like a life of an international student, particularly Iranian students who are going through a lot, of course, and this is just wanted to share with you. And the reason that I dedicated my career to medical research was because of what happened, this tragedy. Now let's get started. In 2015, there was a study in Nature that's showing that the top 10 highest grossing drugs in the United States are only helping 1 out of 25 or 1 out of 4 people who are taking them. So what does this mean? Does it mean that the medication didn't work? No, the medication actually worked, but only for a small group of people. The problem was physicians did not have enough information to predict if the medication would respond positively or not. So let me explain this a little bit. Let's say assume that you want to help me to move from point A to point Z, and we have these 2 options, right? That straight orange line and that windy way. So if I ask you which one is going to be the fastest one, is of course you need traffic, because the accident is going to be important if there is any traffic. If I take that option, that layer from you, then your solution is going to be a guesstimate, of course. When we're talking about human health, our health is a product of microbiome, gut bacteria, our genome, which is our DNA, RNA, and proteins, and we're talking about environment, our lifestyle, our diet. These are all creating our metabolism, all the small molecules in our body. So when we want to make an accurate decision, of course, we need a lot of information. Layers of information here would help us to make a better judgment. And that's an amazing quote from a physician from 2,500 years ago saying, it is more important to know what sort of person has a disease than to know what sort of disease a person has. Now, when you start collecting data, then suddenly the cost function would shift toward computation and storage. On the right side, you see that there's a huge gap between CPU performance versus the amount of data we are collecting. And on the left, here we go. This is Dr. Michael Snyder, chair and professor of genetics. We have collected over 2 petabytes of data around him. And if you want to store 1 petabyte of data on any major cloud provider today, it will cost you roughly around $20,000 per month. So clearly, we need better computational and storage systems. Now, when we talk about deep data needs and challenges, these are the needs. We need data acquisition, data collection. We have data storage. We have classes of storage, cold line. We have hotline, nearline storage. Data distribution is important. Where is it located? Different cities, different continents. Data analysis, AI, ML. But what are the challenges? The first challenge is the scalability, I see. Because when you're talking about precision health, you have to show that your solution works for a large number of participants. You would not be able to publish in any high-profile journals these days without running your solution for a large number of participants. So scalability is, of course, number one. Second is interoperability, which is intertwined with scalability. If your algorithm works for Fitbit, it should work for Apple Watch. If it is working on AWS, it should work on Azure and GCP. The third piece is security and privacy, which is the foundation of any medical application. I refer to scalability as a dragon with multiple heads, because it's not just about infrastructure scalability. There's group scalability, we have organizational scalability, even UI, UX are very important these days. And security and privacy in a medical application is more like an angel of death. When it comes, it's over. But what is the biggest problem? The biggest problem is the gap between engineering department and a School of Medicine. I remember 2014, I went to Duke University, and this biology, a very talented biologist, he started talking about mature RNA, microRNA, messenger RNA. It was so overwhelming for me. It was intimidating. And similarly, I was talking about Apache Spark and distributed computing, and it was challenging for him too. So I see this as the biggest problem still in the School of Medicine. But when we talk about the School of Medicine, this is a major problem, team formation in schools of medicine. If you consider teams in a School of Medicine as a soccer team, and we have these 4 positions, if forward player are data scientists, this is how we are forming teams in the School of Medicine. Everybody want to be Cristiano Ronaldo, Lionel Messi. But who is going to take care of the rest of the field, right? We have data acquisition, storage and processing, scalability team, security and privacy team. So we're talking about larger scale these days, right? Precision health. So this is one of the fundamental problems. We need cross-functional team of experts. The second piece is that global governance. Traditionally, because researchers in the School of Medicine were dealing with a small amount of data, they would assign challenges regarding scalability and security to university IT. And this disruptor will come up with this algorithm, they were like superstar. University IT will take care of it, because it was a small data set. But these days, they have to scale it. And they come up with an algorithm, they go to university IT, hey, I want to scale this algorithm, scale it for me. And they were like, we don't have the resources, we don't have the expertise to do this for you. So there's so much friction here between researchers and university IT. So essentially what we need is that we need to equip researchers so that they would be able to directly deploy their solution on these major cloud providers. And university IT should be a cross-functional team of experts coming from these researchers to set the policies. So there's a great book about this data mesh published by Jean-Marc Degani. Chapter 5 is talking about dynamic equilibrium between domain autonomy and global governance. I'll talk about this projects, you will see what I'm talking here. So I'm going to talk about some of these disruptive solutions that we created. I'm going to talk first about wearable devices. They're all very useful these days. They're helping us to collect a lot of important information like heart rate variability, thank you, Ken, blood oxygen level, and so many other important parameters. So this is a study, a flight study around oxygen saturation. Those of you who have been flying commercial flights, you know that there are different phases. And what's important here is that at a higher altitude, air pressure is low. And FAA, Federal Aviation Agency, set that regulation that limiting cabin pressure to 8,000 feet, meaning that the oxygen that we have in the aircraft at the common cruising altitude is between 30,000 feet to 42,000. So whatever is over 8,000, it seems like you are at 8,000 feet. And at 8,000 feet, air pressure is 75% of what we have at sea level, 75% of that, all right? Let's see what would happen. So this is data from Mike Snyder. He was flying, and on the x-axis, we have the different phases of flight, and the y-axis, we have SpO2, oxygen saturation. As you can see, before the flight, it's just around 99. Then during the takeoff, it goes a little bit down. In the cruising altitude, his oxygen level went down. And this was like, during the landing, it would bounce back, and after that, of course, it would goes back to normal. So what he did was like around 400 days. He was measuring this for multiple flights. So he created his baseline. He knew that, okay, every time that I'm flying, the cruising altitude, my oxygen level will go to this level. But one day he was flying from Frankfurt to Oslo, and then he observed something completely different. So he saw that, wow, my oxygen level is different. The cruising altitude is like around 90. What is going on? And he remembered that 2 weeks before this, he was in Pennsylvania. He was here helping his brother to put up a fence, and he was bitten by a tick. Now he's flying. You can see here that, but he doesn't have any symptom. It's interesting. What's going on? And a day after that, he developed symptom. He has a fever now. And then 3 days after that, he walked into the physician office. So what happened was basically this incubation period. Internally, the immune system was fighting against this virus. They were creating proteins. You don't notice that. And trapping viruses and bacteria. And so basically using this system, we were able to detect Lyme disease. And then he walked into physician office, and the physician was like recommending, prescribe penicillin. But then he was saying that this is Lyme disease, doxycycline is actually better. So you can imagine there was a kind of a tense conversation. Eventually, the physician gave in, and he prescribed doxycycline, and you can see that it went back to normal. So what's important here is that building baseline, super important. You can't create your baseline, then once you deviate from that, you can catch these diseases much earlier. So I met Mike in 2017, and he was like, hey, Amir, we need to pull thousands of participants' data. We need a system to pull data from wearable devices. So we came up with this system called Personal Health Dashboard, published in Nature Communication 2021. And the core idea, so it's a secure platform, and we have done, I'm not going to go through the detail, but we have done a lot of tests, weak scaling, strong scaling. We have done a lot of security tests, like penetration testing on the phone. I would tell you that if it is not the most secure, but it's on the top of the security, among the most secure apps at Stanford University. But one of the key features here, besides from our Kubernetes, all those technologies that we use and all those keys you can see here, was a concept from personalized medicine. We realized that in personalized medicine, we're not comparing your data against other people, right? So what if we transform your data into something unique randomly, right? Because we're going to compare your data against your data. In that way, we can reduce the risk of re-identification significantly. Let's say my data will be shifted 10,000 days to the future, and Ken's data will be shifted 5,300 days to the future. I'll show you more. That will help us a lot in terms of reducing the risk. So we started in 2021. At the beginning of the pandemic, we set up a team and created a team of biologists, computer scientists, and physicians. And in less than 5 months, we were able to pull 5,300 My PhD users. Every one of them has months of data. And the core idea was, okay, we'll build, this is for one participant. This day is the symptom onset day. And we will build baseline. And then if you can see, this is an elevated resting heart rate, as I mentioned. Your body starts fighting with disease infection internally. And we built this algorithm in less than 5 months, because the paper was actually under review for 2 months. And we created 2 algorithms for COVID-19 that could detect COVID-19 10 days and a median of 4 days before first reported symptom. And if we would wait for the university IT, it would take probably 5 years, I don't know. But this was a cross-functional team of experts that we were able to accomplish this and publish in Nature Biomedical Engineering. But then the first step for us here was to see if we can send an alert to participants. Can we do this in real time? That was the key here for us. And we created an alert system. And the one night, it was like a Friday night, myself and one of my intern, who became, later joined our staff full-time, Arash, we started working on a new algorithm to detect COVID-19. And we were like working nonstop. Sunday morning, we came up with this new algorithm, which is super light, called Night Signal. And the core idea behind Night Signal was, you can see here, that we were collecting data on the phone, de-identified, encrypted, send it to the backend, decrypt the data. You can see that data is actually shifted, right, to 2027. We will run the algorithm in the backend, populate alerts, encrypt it, send it to the phone, decrypt it, re-identify it, and present it to the participants. We would not collect any protected health information. It's all based on variables and nothing, no sensitive data. The sensitivity of the algorithms were 80%. And the core idea was like, okay, if we focus on nights, we would get pure resting heart rate, because that's the time that people are resting, right? So we observed that in the phase 1 that, for instance, somebody's sitting and they are like in a stressful meeting, and we consider that as resting heart rate, because the algorithm are only working based on heart rate, right? It may give them a false alert. But by using this technique, we were able to significantly increase the sensitivity of the algorithm and its specificity. The algorithm is super light. It is running on the phone, and it is a live study right now. If you're interested, go ahead and download My PhD in iOS or in Google Play. And we introduce some cool concepts like this DFA, for the first time, like in Nature Medicine, and it was so fun to see computer science concepts are, getting published in Nature Medicine. At any rate, so the algorithm is right now running on the phone, and the PhD platform, My PhD, has been used by multiple universities. UCLA is using it, UPenn, Duke University, and we're recruiting more studies, helping other universities to launch their studies on our platform. If you're interested, if you want to launch a study, please contact my team. All right, the second part of my presentation is going to be I'm going to share one more personal story, and then I will talk about 2 other systems that we design and develop. With respect to collaboration, John C. Maxwell says collaboration is multiplication. When, for those of you who don't, you're not familiar, if you go to csrankings.org and you turn off everything but just click on HPC, you'll see that NC State is ranked 2nd in the entire nation. The reason is that, of course, we have talented professors like Dr. Frank Mueller. That's the number one. The second is that you see that faculty members are collaborating with a lot of great scientists from national lab. But as an Iranian student, unfortunately, when I joined, I was really having a hard time to collaborate with any national lab scientists. Right now, I'm a US citizen, I can collaborate with them, but before it was really hard for me. So in 2015, Dr. Mueller and I wrote a small proposal to AWS, and the title was Boosting the War on Cancer using AWS. And we got $10,000 worth of cloud credit. God bless America. So, after that, I was able to start, using these resources to collaborate with Duke Cancer Institute, UNC Chapel Hill, Illumina then, and finally I got into Stanford. And this is a picture from us, Dr. Mueller on the right side, Mahmoud Parsian, he's a big data lead at Illumina, and Koros Ozer and Alex from Duke Cancer Institute. So I want to talk about another problem that I have observed in the School of Medicine, understanding the behavior of our solution. Understanding the behavior of the problem, or understanding the problem itself, is a whole different level. It may take a while. But we have to understand our solution, because if you don't understand your solution, you're just going to add more complexity to the problem, right? And it would have a really major problem. So you got to think about scalability at early stage. Let me explain this. This is a sectional chart that pilots use, and on this sectional chart, we have 3 airports. This is Palo Alto Airport, this is Moffett Airport, and this is San Jose Airport, Moffett and Palo Alto Airport. And let's assume that we have 2 options here. We have Boeing 747, and we have Cessna 172. And we want to just deliver papers. What we see is that people love to go with complex solutions, libraries. And in this case, when you go with the Boeing 747, thinking that, okay, I'm going to solve all the problems if I go with this sophisticated black box. What's going to happen is that when you are in the research, you may deal with a couple of participants, but later you have to scale your solution. So the first problem is excessive cost. It's 100 times more expensive, right? So when you are in production, then you're going to deal with that problem. The second problem is once you implement your solution, then you're using these APIs, or let's say black box, then you're restricted. Your computation and storage is restricted by the needs of that solution. All right? So for example, in this case, we go with Boeing 747. We would be able to land on Moffett, but it's going to be impossible for us to land on Palo Alto because of a small runway. So it is really important to think about this, right? So you saw that algorithm that you're running on the phone, right? It will help, when you want to scale your solution, like covering underserved community, let's say developing countries, you want to help them. So these are good to think about them, when you are dealing with early stage. All right, so this is Hummingbird. It's a collaboration between VA MVP and NC State, Stanford. VA MVP is a program that they plan to sequence 1 million genomes. And when you are running a system at that scale, right, if you save $1, that means that you're saving $1 million, of course. So it's published in Bioinformatics 2021, and this is the problem that we were trying to solve. So we're dealing with pipelines in bioinformatics. So every stage is an independent tool, executable, and it has its own behavior. Could be a CPU bound, it would be IO bound or memory bound. And we have so many options on the right side, right? So on AWS, for example, we have over 407 instance types. Which one is the cheapest? Which one is the fastest? Which one is going to be the most cost-efficient one? So that was the question that we tried to answer. We created a platform that helped to answer that. Basically, this is what you are dealing, right, on EC2. And this is another collaboration with AWS. And on this one, recently published, it's just one stage of the pipeline. And you can see on the y-axis is execution time in minutes, the cost in dollar, and this is instance family, and this is a number of virtual CPUs. So for one stage of the pipeline, if someone goes and pick I3, which is good mainly for I/O, it's I/O optimized, it costs around $8 versus something going with the C5A with 4 cores. The difference is $7. We're running for a VA MVP, $7 million wasted here. So it's very, very important, such tools would be really helpful. Again, this paper and the tool is available. They're running, you can run it on AWS, you can run it on Azure or GCP, and it would help you to find the cheapest, fastest, and the most cost-efficient instance. The other problem that I have observed is that centralized databases. People love centralized databases in School of Medicine. They want to put everything in one place because it's easy to manage. But the problem is, I have observed, the first one is that some communities are not comfortable with that, like indigenous communities. They don't want to share their data with a centralized database. They want to keep it on their local database. That's number one. The other thing is that at the end of the day, none of these cloud providers are going to dominate the industry. So it has to be, it's going to be all, of course, distributed. So we observed this and we created another platform called Swarm, a federated cloud framework, published in PLOS Computational Biology. It was another collaboration with Dr. Mueller's lab and VA MVP in Stanford. And the core idea was like, okay, if you want to move data across different cloud providers, it would be very expensive. Right now, if you want to move 1 petabyte of data from GCP to Amazon, for example, it would cost you $100,000. Recently, I wanted to move 7 petabytes. It was $700,000. I was like, okay, forget it. So, typical vendor lock-in problem. So, but the question is that when you're working on, let's say, a genomics application, you will see that typically we are focusing on a set of genes or variants, right? Let's say we have 1,000 patients on, let's say Stanford here, NC State is here, you have 1,000 participants on AWS. What if we focus first on this region of interest and first find out if there is any participants with those characteristics? And before I go and talk about Swarm, the other problem is, of course, data redundancy, because every time that you're making a copy, you have to pay more. And the third problem is that every time that you're making a copy, you are increasing security and privacy risk, of course. You have multiple copies, right? So we came up with this system called Swarm that help us to find region of interest. Let's say, for example, we want to focus on a couple of genes or mutations. It will first find out those region of interest and do the computation where the data resides. And if we have to move data, then it will compress that and find out which site is smaller, move it to a secure channel, and do the computation and give you the results. We have done a lot of work here, like on Google BigQuery, Amazon, Athena. Also, it support Apache Presto. Just for this example here, we reduced the cost like 100 million times. We minimized data motion significantly. Of course, there is a time that you will try it, but we get to the break-even point. But it's really helping us a lot with respect to security and privacy. So I want to talk about the last part of my presentation, which is about first, again, I will talk about another personal story, and then I will talk about education. So in 2014, when I was, my wife, she was a patient at Duke University, Duke Cancer Institute. Then I would go to the gym and with my father-in-law. And one day he told me that, hey, Amir, I met this guy, Jim, and he was saying that he was in Iran. I look at him, so this white dude, what is he doing in Iran? I said, hey, Jim, are you an Iranian? He said, no, I was there actually. I'm a professor. I'm a retired professor in educational leadership. I went to Iran and gave a lecture in University of Tehran. And I was so moved by the fact that, oh, wow, this gentleman, in his 70s, he went to Iran and gave a lecture. I was like, hey, I'm a computer scientist. Do you have any problem that I can help you with your computers? And he was like, yes, I have a couple of Macs, that I want to improve, update. And I was like, sure, I can help you. I went to his house to help him with his computers. When I wanted to leave, he said, "Hey Amir, how can I help you?" And I was like, "You already helped me." But he said, "No, you tell me what I can do for you." I said, "Look, this is a situation. My wife she's a patient. I would love to contribute to the field of medicine. I was wondering if you can connect me to some faculty members." And he was like, "Yeah, sure. I have friends at UNC Chapel Hill and Duke Cancer Institute." And that's how, our friendship started. And we would have pizza hangout nights. Every month I would go with Jim, and he came and he gave a talk at NC State in 2016 around educational leadership when I was a VP of Graduate Student Association. And here we go, two of my favorites, Dr. Frank Mueller and Jim L. Morrison. Jim passed away 2 years ago, and his memory and his wisdom has been always with me. And I just want to tell you that, a lot of you are like always in the lab. Just get out of the lab, go ahead and offer your skills to other folks, and then look for serendipities. That's what he said. When I was talking to him, and I was like, wow, how we became friends, and he said that was a serendipity. And anyway, so again, this is a great thing. I had these fantastic mentors. Dr. Mueller has been super, super duper, supportive, and without his help, I would not be able to definitely finish my PhD. And Jim L. Morrison, of course, he helped me a lot. All right, so as I said, when I went to Duke University, I saw this huge gap, and I wanted to do something about it. So when I joined Stanford, the first thing I did, I created a summer internship program. So we would bring computer scientists around the United States. Utsab Ray, he was actually at NC State. And all of these guys, UCLA, we have UCR, Virginia Tech, 2018. In 2019, a lot of other students would come, and we would train them, we create a common language between computer scientists and biologists. And then I created a course in 2020 called Cloud Computing for Biology and Healthcare. It was offered to biologists, Department of Biology, Biomedical Data Science, and Computer Science. And again, we're helping to close the gap as much as we can. Then one of the things I realized in 2020 when we published this Nature Biomedical Engineering paper is that the paper got access over 100,000 times. And if you check these papers in Nature papers, at the bottom of the paper, there are two sections: data availability and code availability. So of course, you have to go ahead, download the data set. You may not even have access to the data set. Then you have to go ahead and configure the code, right? You may not even have the computing capabilities. So it's going to take a long time for you to figure it out. So we waste a lot of time here. So we came up with this system that with one click you can access to code and data. Everything is pre-configured, called Stanford Data Ocean. And I created multiple modules, research modules on the platform. There's like 9 modules. Started teaching those modules to students, and I realized that there is still something here missing. When we are talking about genomics, we're talking about at least 3 layers of information. One layer is about data. We're talking about genes, diseases, and mutations that geneticists are good. The second layer is about statistics, distribution, probabilities, visualization that statisticians are good. And the third layer is about processing and storing large files that computer scientists are good. So when you bundle it together and give it to a computer scientist or a biologist, they will run away. So I was like, okay, can we come up with a modular platform? So we came up with this platform. Again, this is a learn section that we go through research ethics. First teach you how to respect biomedical data, how to handle that, bias and all those things. Then we go through programming basics, what we need in bioinformatics, Python, of course, R. Then we go through data analysis, that we have visualization and statistics, and then cloud computing, of course, and finally through bioinformatics. So all those layers that I mentioned at the beginning, we have data sets and we created modules that you can run. And this is free. If you are interested, feel free to join our platform. There's a QR code here. and we are, also you can earn badges, and we train you to become a bioinformatician. All right, at the end, again, another thing I want to mention, this is one of our success stories. Arash was my intern in 2018. He joined our team, and he has done a lot. And in 2021, he was the first author of this Nature Medicine paper. And here we go is Thomas. He's a third-year medical student that took the class, and I want to play this one for you.
Beck. I'm a third-year medical student at Stanford. And ever since I've been at Stanford, I've gotten really interested on how we could leverage all of the advancements that has been made in computer sciences to improve healthcare. Scalability is definitely an important thing to learn about, because before you set out to build an infrastructure to process your data, you want to know that it's going to be able to help more than just a handful of patients in a feasible manner. And of course, HIPAA compliance and security is important in developing any sort of cloud computing infrastructure, because I think the average person is already a bit hesitant in using this technology because of security concerns. But what I took away from this course is that these infrastructures are actually much more secure than what we have already in the hospitals if properly implemented.
So this is what I'm doing. I'm trying to bridge the gap and see more people like Arash, who are computer scientists understanding, medicine, and at the same time helping biologists and physicians to become familiar with concepts in computer science, so we can create a cross-functional team of experts to deliver solutions when we're dealing with pandemic, like what we did. All right, this is my team, Deep Data Research Center. If you're interested, we're always looking for collaborators. Feel free to check it out, deepdata.stanford.edu. And these are the list of my amazing collaborators and mentors that without their help, I wouldn't be able to accomplish anything. With that being said, this was my presentation. I would be happy to take your questions. Any questions? Yes.
First of all, thank you for the very interesting talk. I was wondering, when you talked about the first example of the wearable sensing predictive algorithm, where the first disease that you predicted was the Lyme's disease, and then after a while you converted that to COVID. I was wondering, and you always took the heartbeat and then the SpO2 of the wearers. I was wondering if there's a correlation between different.
That's a great question.
Things that different.
Absolutely. We focus on heart rate, resting heart rate, but absolutely, like SpO2, we were using pulse oximeter for that example. But for the COVID-19, we were using these wearable devices, just heart rate and step count. But other data types like heart rate variability, as you pointed out, or like, let's say, SpO2, would help us to increase sensitivity of the algorithm. So SpO2 was not in the COVID-19, but in the Lyme disease, yeah, that was just one example around Mike Snyder that we show that SpO2 is also changing. Heart rate is changing, right? And so these are the two major things. And of course, temperature was changing too. Great question. Any other question? How many of you are graduate students? Awesome. That's awesome. There's so many grad students here. And undergrads, of course, we have here.
No more questions? All right, well, thank you very much, Amir.
Thank you. Appreciate it.
So if you're just shy, maybe you have a question you didn't want to ask in front of everybody, Dr. Bahmani is going to be around for a few minutes. He'll certainly talk with you if you'd like to come up and ask a question or engage with him. I just want to say again, thank you for coming out tonight. Again, the series will relaunch again in the spring. If you would raise your hand, sir, if you're a grad student and you need to check in, if you haven't, if you'll see this gentleman here, if you need something signed, I'll be down front and I'll sign it. Otherwise, thank you again for coming, and we'll see you in the spring.